Hi everyone, I'm Adam Eisen, a graduate student in Earl Miller and Ela Feet's labs at MIT, and I'm very excited to be discussing with you today how we can use the framework of dynamic stability to investigate how propofol anesthesia is disrupting consciousness. This work uses data collected from non-human primates in the Miller lab by Jake Donoghue and collaborators. Here we have sample LFP traces from each of 4 regions of interest: parietal cortex, auditory cortex, frontal eye fields, and prefrontal cortex during both a wakeful state and an anesthetic state. And you can see quite clearly here already that the LFP during anesthesia is qualitatively very different. But what we'd like to do is characterize mathematically what's changing in the LFPs during loss of consciousness, and hopefully this will give us some insight into the mechanism of loss of consciousness due to propofol anesthesia. Now, the mathematical toolset we're going to use to do this is dynamic stability. In a system that is dynamically stable, the distance between 2 initial conditions is going to shrink as the trajectories evolve. And in an unstable system, we'd find the opposite. Over time, the trajectories are going to be growing farther apart. So by tracking how the system evolves, we can get a sense of how much stability is present. There's been some great previous work analyzing neural anesthesia data through the lens of stability, notably Solovey et al. And Toker et al., but these papers actually disagree on the direction of change in stability, with one suggesting stability increases during anesthesia and one suggesting stability decreases. We're hoping to settle this disagreement. Our analysis here is unique, and that we'll be using both linear and nonlinear methods, and we'll be using electrophysiology data. In order to assess the dynamic stability of the system, we're going to treat the recordings as a dynamical system. At each millisecond in the trial, the vector of LFPs represents a point in a neural state space, and the sequence of vectors of LFPs constitutes a trajectory of the system. What we can do is fit a linear model to the data. We're using one-step vector autoregression and fitting this matrix A to predict every time point from the previous time point plus some Gaussian noise. The absolute values of the eigenvalues of A are called criticality indices, and we can use them to assess stability. A criticality index less than 1 corresponds to stable dynamics, and an index greater than 1 corresponds to unstable dynamics. Importantly though, even below 1, the closer to 1 the criticality index is, the more unstable the system. Since the linear approximation only works locally on small timescales, we chunk the data into windows and then fit a VAR model to each of these windows. And we chose a window size of 2.5 seconds based on the model's mean squared error in one-step prediction. So on the x-axis is time in the trial in minutes, and on the y-axis is the mean criticality index for each window across all 4 brain regions. Also, we have the drug infusion portion in purple, as well as the time of loss of consciousness in red, and the time of return of consciousness in green. And what we see here in monkey 1 is that the more stable regions during wakefulness, prefrontal cortex and frontal eye fields, undergo a rapid destabilization during the onset of anesthesia, followed by a return to more stable dynamics after anesthesia ends. And in the top right corner is additional data from a second monkey, and here we see again that there is a robust destabilization in prefrontal cortex during anesthesia, but now we actually see this across all brain regions. Now, the VAR model is one of the simplest we could think of using, and we wanted to check that a more modern method rooted in machine learning would reproduce qualitatively the same findings. So we turned to using a switching linear dynamical system, or SLDS, in place of vector autoregression, which enables us to add some nonlinearity into the dynamics. The SLDS treats the LFP data as high-dimensional observations from a system with some underlying low-dimensional activity, dependent on a discrete state. And the key here is that the transition dynamics switch based on the discrete state. So the advantage of this model is instead of relying on locally linear approximations, we can approximate nonlinear dynamics by switching between different linear dynamical systems. So here we have the results from fitting a switching linear dynamical system to 5-second windows of VLPFC data in monkey 1. Again, on the x-axis we have time in the trial in minutes, and on the y-axis the mean criticality index, as well as drug infusion in purple, loss of consciousness in red, and return of consciousness in green. And what we find here is the same pattern of destabilization of activity in prefrontal cortex after the onset of anesthesia, followed by an increase in stability as the animal emerges from unconsciousness. And interestingly, all the criticality indices are much closer to 1, with the values during anesthesia being extremely close to 1. suggesting that anesthesia drives activity in prefrontal cortex to be maximally unstable without exploding to infinity. The main takeaway we can get from our analysis is that propofol destabilizes activity in prefrontal cortex. And this suggests stable information flow as a potentially essential component of conscious processing. And of course, there's still lots of work to do here. So just lastly, many thanks to my close collaborator Leo KOZACHKOV for his patience and wisdom, to Earl Miller for his insightful guidance and interpretation, to Laffitte for many helpful discussions, and to the collaborators on this project for all their fantastic work on data collection and analysis prior to this. So thank you very much.